You're falling toward a black hole and you cross the event horizon, the point of no return. But here's what's genuinely weird. According to physics, you both do and don't cross it. From your perspective, you cross in minutes or hours. From an outside observer's perspective, you never cross at all. And both versions are completely true. If that sounds impossible, that's because our everyday experience of reality breaks down completely at the edge of a black hole. What actually happens when you cross the event horizon isn't just counterintuitive. It's the kind of thing that made Einstein himself uncomfortable with his own equations. Let's start with what a black hole actually is, because the popular image gets it wrong. A black hole isn't a cosmic vacuum cleaner sucking everything up. It's not even really a hole. It's what happens when gravity wins so completely that it breaks the rules of space and time themselves. Picture the most massive stars in the universe, at least 20 times heavier than our Sun. For millions of years, these stellar giants maintain a perfect balance. Nuclear fusion in their cores pushes outward with tremendous force, while gravity pulls inward with equal strength. It's like an eternal arm wrestling match between two cosmic forces. But eventually, the fuel runs out, the fusion stops. And gravity never gets tired. When that balance breaks, the star doesn't just collapse, it catastrophically implodes. The core, which was once thousands of kilometers across, gets compressed down to an incredibly dense point. The matter gets crushed into this point, along with the very fabric of space and time around it. We call this a singularity, and it's where our understanding of physics simply stops working. But here's the crucial part. The singularity is at the very center of what we call a black hole. The black hole is the entire region of space around the singularity, where something very specific happens to the fabric of reality. At a certain distance from the singularity, different for each black hole depending on its mass, space and time become so warped that they create a one-way barrier. This barrier is the event horizon. Think of the event horizon like a waterfall. If you're in a canoe upstream, you can paddle against the current and stay in place, or even go backward. But once you go over the edge of the waterfall, no amount of paddling will get you back upstream. The event horizon works the same way, except instead of water flowing over a cliff, it's space itself that's so warped that nothing, not even light, can escape once you cross this boundary. For a black hole with the mass of our Sun, this point of no return sits about 3 kilometers from the center, what we call the Schwarzschild radius. For the supermassive black hole at the center of our galaxy, which weighs as much as 4 million suns, the event horizon is about 12 million kilometers across. That's roughly the size of Mercury's orbit. Now let's say you're approaching one of these monsters in a spacecraft. You've decided to cross the event horizon and see what happens. But here's where things get genuinely strange. What happens depends entirely on who's asking. Let's follow your journey from two perspectives, yours as you fall in, and that of your friend watching from a safe distance. From your perspective, falling toward the black hole feels surprisingly normal at first. If it's a supermassive black hole, the kind you'd actually want to fall into if you had to choose, you won't feel anything unusual as you approach the event horizon. You're in free fall, which means you feel weightless, just like an astronaut in orbit. The view, though, spectacular and terrifying. As you fall, the black hole grows larger in your field of vision, but it's not like approaching a planet. There's no surface, no features, just a perfectly black sphere that seems to absorb light itself. The space around it looks distorted, like looking through a funhouse mirror. Stars behind the black hole appear stretched and duplicated as their light bends around the massive object. As you get closer to the event horizon, these optical effects become more dramatic. The black hole begins to dominate your view, and the stars behind you appear to compress into a bright ring. This isn't science fiction, it's exactly what Einstein's equations predict light should do in such extreme gravitational fields. Then you cross the event horizon, and here's the thing, you don't feel it happen. There's no barrier, no wall, no sudden change. One moment you're outside, the next moment you're inside, and the only way you'd know is by looking at your instruments. The event horizon isn't a physical barrier you can touch, it's a boundary defined by the geometry of curved space-time itself. But now you're doomed. Not eventually doomed, not probably doomed, absolutely, certainly, mathematically doomed. No force in the universe can prevent you from reaching the singularity at the center. You have maybe minutes or hours left, depending on the black hole's size. Now let's rewind and watch the same event from your friend's perspective, safely positioned far from the black hole. Your friend sees something completely different. As you approach the event horizon, your friend notices that you appear to slow down. The light from your spacecraft becomes redder and dimmer. This isn't an illusion, it's a real effect of gravity on light and time. Here's what's happening. As you get closer to the black hole, time itself runs slower relative to your friend's reference frame. Your friend's clocks tick normally, but your clocks and everything about you runs slower and slower. The light leaving your spacecraft has to climb out of an increasingly deep gravitational well, losing energy and becoming redder in the process. From your friend's perspective, you never actually cross the event horizon. You appear to slow down more and more, your image getting redder and dimmer until you fade away completely. Your friend could watch for billions of years and never see you cross that boundary. But remember, from your perspective, you crossed the event horizon and hit the singularity in a matter of minutes or hours. Both perspectives are completely correct. This isn't a limitation of our measurement tools or a failure of our theories. This is what actually happens according to our best understanding of space and time. The event is simultaneous and non-simultaneous depending on where you're standing when you observe it. But we've been assuming you survive to cross the event horizon, and that's a big assumption. Whether you make it that far depends entirely on the size of the black hole you're falling into. Remember, gravity doesn't just pull on you as a whole, it pulls differently on different parts of your body. Your feet, being closer to the black hole, experience stronger gravity than your head. This difference in gravitational pull is called a tidal force, and it's what creates tides on Earth as the Moon pulls more strongly on the side of Earth facing it. Near a black hole, these tidal forces become extreme. The technical term for what happens to you is spaghettification, which is both accurate and terrifying. You get stretched lengthwise and compressed sideways, like being turned into a piece of spaghetti. For a black hole with the mass of our Sun, these tidal forces become lethal when you're still about 600 kilometers away from the event horizon. The event horizon itself is only about 3 kilometers from the center, so you'd be ripped apart long before you could cross the point of no return. But here's where size matters dramatically. Tidal forces depend on how quickly gravity changes with distance, and for larger black holes, gravity changes more gradually. The supermassive black hole at the center of our galaxy is so large that you could cross its event horizon and not feel dangerous tidal forces until you're much closer to the singularity. This creates a bizarre situation. You're more likely to survive crossing the event horizon of a monster black hole millions of times more massive than our Sun than you are a small black hole just a few times heavier than the Sun. Even if you survive the crossing, your fate is sealed. Inside the event horizon, all paths lead to the singularity. This isn't just difficult to escape from, it's geometrically impossible. The structure of space and time inside the event horizon is such that moving away from the singularity is like trying to move backward in time. Every direction you can travel, including staying perfectly still, leads you closer to the center. What happens at the singularity itself? Honestly, we don't know. Our equations break down completely. Some physicists think you'd be crushed to infinite density. Others believe quantum effects we don't understand yet would prevent this. Still others think you might emerge in another universe entirely. At this point, we're beyond the edge of established science and into educated speculation. But there's another complication that makes this even weirder. Some recent theoretical work suggests that the event horizon itself might not be as simple as we thought. The firewall paradox in physics proposes that quantum effects might create a wall of high-energy particles right at the event horizon, meaning you'd be incinerated the moment you tried to cross, rather than gently falling through. This paradox arises from trying to reconcile Einstein's general relativity with quantum mechanics, and physicists are still debating whether firewalls actually exist or if there's some other resolution to the paradox. You might be thinking, this is fascinating, but when am I ever going to encounter a black hole? The nearest known black hole is over 1,500 light-years away, so you're not in immediate danger. But understanding what happens at the event horizon tells us something profound about the nature of reality itself. The fact that two observers can have completely different yet equally valid experiences of the same event challenges our basic intuitions about how the universe works. In our daily lives, we assume that events either happen or they don't, and that everyone should agree on when they happen. Black holes show us that this assumption breaks down under extreme conditions. This isn't just academic. The same principles that govern black hole event horizons apply to other extreme environments in the universe. The edge of the observable universe, for instance, acts like a kind of event horizon. There are parts of the universe we can never see because light from them can never reach us. Understanding black holes helps us understand the fundamental limits of knowledge itself. More practically, black holes are the engines that power some of the most energetic phenomena in the universe. The supermassive black holes at the centers of galaxies shape how those galaxies evolve. The collision of black holes creates gravitational waves that we can now detect on Earth, ripples in space and time itself that carry information about events happening billions of light-years away. And studying black holes pushes us to develop new physics. The contradictions between general relativity and quantum mechanics that show up at event horizons are clues that we need a deeper theory. A quantum theory of gravity that could revolutionize our understanding of space, time, and matter. Even the technology we use to study black holes has practical applications. The algorithms developed to process data from the Event Horizon Telescope, which gave us our first actual image of a black hole's event horizon, are now being used in medical imaging and other fields. So here's what would really happen if you crossed the event horizon of a black hole. From your perspective, you'd fall through in minutes or hours, experiencing the universe's most extreme environment before being crushed at the singularity. From an outside observer's perspective, you'd never cross at all. You'd simply fade away at the boundary, frozen in time forever. Both stories are true. Both happen. The universe doesn't choose between them. It contains both realities at once. That's not a failure of our understanding. It's a feature of how space and time actually work under the most extreme conditions imaginable. The event horizon isn't just a boundary in space. It's a boundary of reality itself, where our everyday concepts of cause and effect, before and after, inside and outside, simply stop making sense in the way we expect them to. And perhaps that's the most mind-bending thing about black holes. They don't just challenge our technology or our mathematics. They challenge our most basic assumptions about what it means for something to be real.